Okay, we start our session now. We go to chapter 7.6, sinusoidal detection, and it's at page 261. So for you, makes it easier for you to follow. Okay, if you can follow the page number. So the detection of a sinusoid in white Gaussian noise is a common problem in many fields. Because of its wide practical utility, we examine in some detail the detector structure as well as their performance. The results form the basis for many practical sonar, radar, and communication systems. The general detection problem is H0 xn equal to Wn. That is a noise only signal. And H1 is Xn equal to Wn, and for n is 0, go to n0 minus 1, and then n0 plus m all the way to n minus 1, with another uh, another signal in it, and that signal is a cosine a cosine 2 pi f0. N is the time index. Okay, this is a time index plus phi, that's the phase, and then plus noise. So that is from n is equal to n0 to n0 plus n minus 1. Okay, so where the Wn is the white Gaussian noise with non-variance sigma square. And any subset of the parameter set, see, we have amplitude, frequency, and phase may be unknown. The sinusoid is assumed to be non-zero over the interval, with m denoting the signal length and n0 the delay time. M is the signal length and n0 the delay time. Initially, we will assume that n0 is known and that n0 is 0. The observation interval is then just the signal interval, or this. Okay, so that's the observation interval. And later we will allow for unknown time delays. We now consider this, which is what? Which is there's no delay problem here. Okay, no delay problem, because it's either noise or noise plus signal, and that signal starts from n equal to 0, so it initiates at the beginning. So the signal is not does not have any delay. Where the but the unknown parameters are deterministic, and it's compared to some sections we talk about Bayesian approach where the parameters are random variables, but here, yes, they are deterministic. So, but we call that those are unknown, but model as realization of random variable. That's the Bayes approach. That's the Bayes approach. But our approach assumes it's deterministic, so we will be using GLRT for some cases. First one, A unknown, A phi unknown, A phi 0 unknown, and then A phi F0 N0 unknown. So you have a variety of combinations of what's known and what's unknown. Okay, so let's first look at the first problem. We have that the signal is AS, where S is equal to cosine, is a sinusoid. Then in sinusoidal signal, cosine and sine are interchangeable just by changing the phase. So it's the same as if you're doing sine. And Sn is known. This is exactly the case studied in 7.4, right? Previous. Typically, the sign of the amplitude is not known. That's from this we decide H1 if this is larger uh, than gamma prime. This is you do the correlation. You do the correlation and then take the square. So yeah. So let's go back a little bit. It's derived before 7.13. Right? It's derived. Then we're not redoing the process, but the test statistic is the correlation and then take the square. So we are doing this received signal correlate with the known signal and then take the square larger than gamma prime. With the detection parameters given by the MLE of the amplitude is like this, and this is again done before. Right? So you do correlation and divide it by cosine square, and then 2 divided by n summation x at cosine. Okay. For f0 not near this, the detection is shown at and its performance is given in. Here we have this is sort of SNR, kind of like SNR. Okay, so what that means is let's review a little bit. What we want to do is, if you're given that signal model, you do this and then decide H1. If smaller, then you decide H0. Okay, so it's the two options. And then what do you do with that A? What do you do with that A? You do this, and this is done somewhere in a estimation textbook, but we're going to do it a little bit later. Then amplitude and phase unknown. So when A and phase are unknown, we must assume that A is larger than 0. Otherwise, two different sets of A phi will yield the same signal, and that's the parameter will not be identifiable. The reader should consider what happens if A is equal to 1 and phi 0 or S minus 1, phi minus pi. In fact, they are the same thing. If you imagine you have a cosine and you have a minus cosine, the difference is the phase are changed by 180 degrees. So you put a pi in a different cosine and they will be identical. This is called ambiguity. Not identifiable. In a lot of places, it's ambiguity. Ambiguity. So in a lot of scenarios, we could have this ambiguity situation, but it's kind of like a symmetric structure in the signal. So it can be easily resolved though in practice. In practice, it can be easily resolved. So we just make a slight assumptions to make it disappear, just for the ease of a discussion. I think it's fine. The GLRT decides H1 if this is that, right? And P of X A phi H1, and then A phi is MLE, and F0 is not near. It's cancelled out. It's cancelled out. Hence, we decide H1 if this likelihood ratio is larger than gamma, LGX equal to this divided by this. Okay, you have this that goes here. You have this that goes here. And of course, those things needs to be derived first. Right? But that's not the key of our discussion in this in this, but we'll just use it. We just use it. So you have this Gaussian distribution with x minus a cosine, and then p of x h0. The MLE for large n can be shown to be approximately this and this, where uh, alpha 1 hat, alpha 2 hat, and alpha 2 hat minus over alpha 1 hat. Alpha 1 hat is composed of x correlate with the signal, and alpha 2 is x correlated with the signal, and that signal is cosine, that signal is sine. There, as we said, there's a 90-degree difference in the phase, and alpha 1 defined this way, alpha 2 defined this way, and then you use alpha 1, alpha 2 to calculate phi hat and a hat. Use phi hat and a hat to put it in, and then you get this pxa phi h1, and you get this px h0 here, and then you do the derivation, you get this glrt. Okay, so now we uh, take a little bit looking at these figures. This is a GLRT for sinusoidal detection. GLRT for sinusoidal detection for unknown amplitude and phase, unknown amplitude, phase and frequency, unknown amplitude, phase, frequency, and arrival time. So you have a lot of different combinations. Okay, so if you see the first one, that's unknown amplitude. Unknown amplitude, what you do is you correlate with that. You correlate your received signal with your sinusoidal signal, and you multiply, and summation is a correlate, right? The whole thing is a correlate. And then you take the square, and then you compare with that. And when you do the comparison, if it's h1, then you do this. You get a hat. Unknown amplitude. Unknown amplitude and phase, you have it here. Right? You have it here. So what you do is you want to implement this. This is going to, let me see. You go to here, and we have not derived it yet. So let's take one step further. In deriving the MLE parameter transformation, right? As we mentioned, there you have alpha 1 and alpha 2. You have alpha 1, alpha 2. So you take the log likelihood over G, and then it becomes, do some reduction. If you do reduction, those kind of things disappear, and the rest remains, but you can cancel the s square. So that you get this a x with cosine and a square with cosine square. Using the parameter transformation, we have alpha 1 equal to a cosine and alpha 2 minus a sine, so that this thing is becoming, with derivations, becoming that. And then we make use of this summation cosine approaching n by 2 results in lng. lng becomes, let's see, lng is now reduced to this, right? So you have x a cosine and a square cosine square, but with those reductions, xa cosine here, becoming this, right? Summation cosine square becoming this. So now you have ln g equal to this and this. That is because this term is replaced by this, and this term is replaced by this. So you get something like that. And uh, then you continue on with that. You get like this, and then you get that. Okay. And then how come that a squared disappear? Because it's irrelevant, right? It's irrelevant in terms of calculating the maximum of this likelihood. It doesn't matter that much. So you put it either in the right hand side or it just disappear. So we decide one if that is like that. But this thing, we decompose it, we find it to be x cosine and x sine, and it becomes like this. Okay, then it can be written as 4 minus divided by n if0. And what is if0? If0 is a periodogram evaluated at this, but disregard the terminology of this. We just take it as a mathematical formula, and then we just consider that as a as a function. But if we take a transformative perspective, this is actually a transformation of x being transformed by this basis, right? And this basis is something like a Gaussian basis, not Gaussian, but the Fourier basis, right? This is something like Fourier basis, but that's in the signals and systems, so if you're not familiar with it, it's fine. We just take it as a function and then evaluate it here. So the form of the detector is identical to that for the Rayleigh-Fading model. Of course, the detecting performance will be different. This detector also called the incoherent or conjecture match filter. Okay, conjecture match filter. In other words, IF0, which is something like this, this is x multiplied by exponent, but exponent can be decomposed into cosine and sine, right? Therefore, I0 can be decomposed into two components, this component, that component, and this one is the cosine, one is the sine. One is the cosine and sine. As a result, there are linear transformations of x transformed by what? By cosine and sine, right? And for f0, it can be shown that uh, this cosine is n dot or Gaussian distribution by this and this. Okay, that's why when we take a look at this, you see you have x. Okay, let's take it a little bit slow. Here, we're talking about unknown. We're talking about unknown amplitude and phase. Okay, amplitude and phase are known, and eventually, step by step, going through the process, we go to the point of this, right? This. So you have to do cosine square, then cosine is x multiplied by cosine, x multiplied by cosine. So if we go back to this figure. This figure is to implement conjecture, the conjecture stuff. And that conjecture stuff is composed of x and cosine, x and sine, right? And sum together and take the square and do a summation, and you get the periodogram, right? And you compare with the threshold, and then do the final decision. That's a conjecture version of it. And what is that? Here. That is here. This is called conjecture mesh filter. Here. Okay. And then continue with the derivation. Eventually, it goes to this is under h0 is 0 and that, or it's that mean and that. Okay. As things under either hypothesis, the random variables are independent. The PDF relate to central chi-square under H0, right? This is central chi-square under H0, and non-central under H1 because it's this. Specifically, consider normalized periodogram. Remember that periodogram has a square term, has a square. So whenever we talk about Cauchy, they are Gaussian, then you take the square, you take the sum, then you get chi-square. Okay? Recall that chi-square, where does it come from? It comes from Gaussian square, right? Or summation of Gaussian square come to chi-square. Okay? If this is not clear, then refer to chapter 2 to 3 when we talk about spatial distributions. Okay? And then chi-square under H0 and non-central chi-square under H1. Specifically, consider the normalized periodogram. The latter is distributed as chi-square PDF under H0 and chi-square lambda under H1, where the lambda is like this. Okay, that's a non-centrality parameter. Okay, so up to this point, we will be able to explain the other structure. The other structure. That is the periodogram structure. You have x, then you want to multiply with the exponent, and then you sum it up. You take the square, sum it up, divide it, you get I0, and then you do that. So exactly this and this is the same, except the implementation is different, but they are mathematically identical. Okay, now you get a chi-square distribution for H0, chi-square distribution for H1. Now PFA is when, because you are doing the threshold for gamma, so PFA is the probability IF0 larger than gamma prime condition on H0, because that's when you will do what? That's when you do H1, right? That's when you do H1. So that's the thing. And then you continue on with the derivation. Eventually it goes to chi-square Q function and exponent of this. And PD is when you have H1 and you do decision for H1. That's a correct decision, which is good. And then you do the derivation, you go to the chi-square. So in summary, the detection performance it will be written as this PD chi-square like that, where lambda is like this. Okay, so we'll just stop here for the moment and we'll come back in a little bit.